All right, thank you very much. I knew this would be a broad audience, so I'm keeping it broad. And if you have any questions, raise your hand, stop me, and I will speak back to you and address whatever you want clarified or repeated or not said at all. As Thorsten said, the last presentation that I gave where he was at, he told me afterwards it was the most boring thing he'd ever heard, so I decided to change all my slides and completely throw all that work away for another time. So through the ocean, that's our world's oceans, to the mantle, that's the solid Earth, the mantle of the Earth. And I haven't actually added them up. It may not have been quite 20,000 leagues. A league is a nautical mile of some description. But we have done quite a distance under the ocean surface with a fleet of robots, if you want, with recorders that record earthquake activity. And so that explains my title. This is just my name on this slide, but it's not my name. Many other names are coming up. I'm referencing them very small, but I will bring them up as they loom larger. Clearly, I'm not alone here. And I want to give plenty of credit here. So the very, very big picture, we have the Earth. It's a ball of stuff. It's chemically differentiated. It's not all made of the same stuff. And the stuff that is of different composition or different phases or different materials and property is in different places. This is a major aspect of our Earth. And it's also physically deformed and deforming, actively deforming. Earthquakes do this ongoing geodetically measured tectonic deformation. And however the chemistry and the physics conspire to put stuff in different places and in different forms and shape, they alter the properties of the Earth in such a way that can be measured by the three main branches of what I call solid Earth geophysics, namely whatever happens, whatever changes, whatever deforms affects the speed of seismic waves, the elastic wave speeds and the anelastic aspects of it, which cause earthquake waves to go to different places at different rates depending on what they go through. These property variations cause what we call anomalies in the Earth's gravitational field. It isn't all and everywhere 9.81 meters per second square for the gravitational acceleration, because the Earth is made up of all sorts of different things on the inside and on its surface that are detectable very, very well, including their time changes. And then finally, something that I won't talk much about today, but if you want to summarize a whole lot of what's going on in the Earth, just looking at its shape, it can be remarkably revealing. Whatever happens inside in terms of mantle convection that Thorsten and others study here, well, that has its imprint on what the surface records as topography. So I like to think that if we understand Earth or any planet, the first thing we have to do is to go look at these three physical observables. Clearly for other planets we won't be having any chemical measurements anytime soon. Seismic velocities, so that's a broad field of structural seismology, as Thorsten just called it, which includes attenuation, how the quality of the rocks may not be quite as high to transmit sound speed or elastic wave speeds as faithfully everywhere without any loss. And then the very important directional or polarization dependence of seismic waves, which is expressed as seismic anisotropy, which comes about because rocks are deformed and rocks contain minerals, and minerals transmit waves in different directions and with different polarizations at different speeds. So that connects subsurface geology all the way to the large-scale makeup of global seismology. Then something I won't be talking at all about today is the gravitational anomalies of the Earth, but I have done quite I have a big interest in monitoring the Earth's satellites for what their time-varying geopotential reveals about the surface and subsurface properties of the Earth. So gravity anomalies, just the presence of a denser material at depth will create an anomalous piece of gravity. It will have a dynamic expression because the Earth on the inside is already deforming, and so that warps down interior interfaces. And then all of that stuff is time dependent because we are melting ice caps as we speak by burning all that oil that you are all helping us find. The time dependence of gravity is now a prime observational tool to look at shrinking ice caps and rising sea level, which I won't talk about today. And then finally, again, topography, just to look at the shape of the Earth and the record of its, as a records of its interior, and then clearly and including its interactions of, with atmospheres and oceans is of major importance. So what I'm going to do is, oh, and then I left that last bit out. I do study those things, and I think they're only getting interesting when we correlate one with the other, when inference from one field can be used to look at what it implies about another field and vice versa. And so the notion of statistical correlations, of cross-dependence, of the joint description of these parameters is what really gives us the knowledge, and that implies also a breakdown at different scales, which means different spatial footprints and different wavelengths if we deal in spatial wavelengths, which we do. So a few gratuitous pictures. The Earth's topography, how high or low the physical shape of the Earth is above a gravitational reference. Okay, this is not just geometry, this is with respect to an equipotential surface of gravity. The Earth's gravity, if you see any pictures, it'll typically be a gravitational anomaly. This is an example of an older model that tells you if all things are being equal and we take out the big effects of the flattening and the rotation and the ellipsoidal shape of the Earth and we refer everything to a common proper geopotential, then we still have important anomalies. And here is a first relatively crude image of those things, which of course reveals plate tectonics right away. The big mountain change and arcs and subduction zones are all mapped by just plotting on the in this plot what the gravitational anomalies are. And then finally, seismology. Well, I'm not going to show you just a picture of the wave speeds yet, but here let's just take a look at the occurrence of the earthquakes. They are, of course, also clearly defining the plate boundaries with the odd intraplate earthquake. And you, in your various courses and classes and research projects, are probably much more experts about different subsets of them. The point is they're everywhere, but not all the time. We have had a string of recent ones. They're not everywhere because they have specific reasons for being in specific places and then not in others. So, thermodynamics, physics, chemistry, temperature is an important descriptor of what's going on in the Earth. The Earth is a heat engine. It's getting rid of whatever heat is being generated by radioactivity and whatever was left over from its formation and whatever other little bits it acquires due to phase changes. Chemistry, what material, what elements, and in what shape, mineral form, or phase they are, that affects what we are able to study. And my only physical variables are density and the elastic constants that together with density define the seismic velocities. And that's why we study seismology, to work that arrow back up to back out what the temperature and compositional state and state over time evolution is of the interior of the Earth. And we'd be lucky if one day we'd know as much about another planet as we know about our Earth. And a couple of years from now, I'm sure you'll hear talks about the Mars InSight mission, which is going to put a seismometer on Mars if they are lucky. Last slide here on the general concept here. Well, I like to show this picture to students, you know, an earthquake, okay? It's recorded at different seismometers, and the very fact that we record evidence of phases, you know, P waves and S waves that, you know, bend and come back up, that immediately tells us that their wave speeds in general increase with depth thanks to optical refraction. They come back up. In some places we see sharp reflections like this, let's say 400 or 220 or 500 or 670 discontinuities. Seismic waves hit certain very specific boundaries and they bounce right back up. And so reflections tell us about physical chemistry inside of the Earth. The existence or not of waves, the existence or not of certain types of waves immediately tells us that some parts of the Earth are actually fluid, like the outer core of the Earth, and then solid again like the inner core and the innermost inner core of the Earth. And none of that we would know without seismology. I actually need to make a switch from this to this. And here, For a very long time now, we have had a very good reference model for what those wave speeds of the Earth are doing. I started by saying the Earth is chemically differentiated and physically deformed. Well, it exists like a layer of concentric shells that are to first order pretty well modeled by a crust in 2 layers, and then an upper mantle transition zone, lower mantle. And here I'm plotting 3 popular reference models that we're all using to describe the first order aspects of recording any earthquake seismometry at all, and they're all doing a pretty good job. They're not the same, so the statistician in me wants to say, well, which one is it, guys, because it's, you know, plus or minus, and the differences here are revealing uncertainty, yes, noise, statistics, not doing the right thing, not knowing everything, but of course also the heterogeneity, because the Earth is made up of continents and oceans and mantle and core and crust, and the fact that not any single radially variable, one-dimensional, in other words, Earth model captures it all, well, inevitably that leads to differences between those models. So both uncertainty and also just heterogeneity. So we need to go from the 1D Earth to the 3D Earth. And here's another way of looking at this. This is a record section. This is on the x-axis here is as a function of x. We have the distance across, measured across the surface of the Earth, so in degrees. So 90 degrees is like a right angle pointing to the center of the Earth, and then all the way around to the antipode. And so just turning the seismometers on, recording where the earthquakes are, referring the time to the right place, and not wondering or adjusting in any way where those seismometers are, and just plotting the results on top of one another, shows you that there is these clear phases. And let's just take a look at the P wave here. You see that, you know, it has a predictable arrival, very, very well described by those radial reference Earth models. But of course, it's in the scatter here, that fatness of that black line, the couple of seconds of faster and slower, that's where all the information lies. So if you're in exoplanets and you have this, you'd be ecstatic. You'd be really, really happy. You'd know a lot about your exoplanet. But on Earth, this is old hat from the 80s. We are now interested in the very, very slight seconds differences that these phases take to arrive from the earthquake to the station because of interior heterogeneity, which we want to get at. Okay, and clearly if you're taking a whole class on seismology, you're going to see the complete richness of phases. They're a little grayed out here, but you still see lines coming through there with bounces and surface waves and inner core waves and all those particular things which seismologists clip out and invert for specific things, specific aspects of the structure. So I like to show this, this picture here. This is some record of some earthquake somewhere, and you'd recognize some sort of a body wave phase and some sort of a larger surface wave arrival. And one of the colors, black, is the data, and the other one is a spectral element simulation, which is a particular technique of seismic wave propagation that the likes of Professor Grant here uses to do his tomography. And overall, anybody with a good computer and a location of an earthquake and a station can do a pretty good job at predicting what sort of record we would be getting. Except that in some places, you know, the model prescribes or tells us that, you know, that is expected a little early, or it's a little too big, or is a little phase difference, or the frequency doesn't quite match. But you all recognize that those two records are living on the same planet, and the model does, without any other adjustments, a reasonable job as a starting model. And if we now manage to adjust the velocities in the interior of the Earth just a little bit here, a little bit there in their impact on time, then we can fit the Earth structure to this one and then hundreds and ultimately thousands of observations to adjust that 1D Earth model into a three-dimensional model that tells us more or less what's going on the inside. So broadly speaking, that is the art of looking at a record, trying to see what our prediction does well, much of it, figuring out what to measure, how to measure, and what to adjust for in a process called inversion. It's called tomography. It's the art of slicing, okay? Not different like X-ray tomography. As soon as people had worked out how to do the computation of X-ray tomography in the 70s or late 60s, digital seismometry, other seismometry came into play, and pretty soon thereafter seismologists were at it trying to image the interior of our own planet. It's so much more interesting in the Earth than it is in the medical applications, because we measure waveforms, we don't just measure intensities. We shoot complex earthquakes, long, evolving slip patches, slow and fast, large and small. The waves bounce all over the place. The records are incredibly varied. They're not straight paths. They're not a controlled experiment. And so seismic tomography draws back upon the X-ray tomography, but the richness of information and the richness of techniques is just so much greater. With the drawback, obviously, and a point that I want to make right away, is that when you're in a doctor's office and they tell you take your clothes off, you just do it. Put yourself down, let yourself be surrounded, like you have no choice. They have completely experimental control over you. When we tell our Earth, please show us your inside, they won't just do it. We don't control where earthquakes are happening, and while we can try, we really do not completely control where we put seismometers that record ground motion, for the simple reason that where it's wet, it's hard. So we have a lot of seismometry on land and not very much in the oceans. Okay? So the analogy with X-rays goes only so far, and the principal difference here is that we don't have experimental control. It's like trying to image the inside of a patient with one eye, or with one X-ray detector, or no changing sources or something like that. Couple of cartoons, you know, some earthquake from somewhere recorded somewhere else. Well, that describes a well-known path to or from which to first order. It's pretty much, that's the arc that the earthquake will take. Yes, there will be deviations precisely because there is 3D structure, but to first order, we're ignoring the path difference, and we're starting right away by dividing the Earth in some parameterization, not necessarily cells, but they could be like that. And here I'm just shading the path length that they take just to get a rough picture of, well, where it's been, we're going to have some information. Where it's not, we still have some information, but to first order, it's away from the sampling. One earthquake, one data. Of course, we need hundreds, if not thousands, and we do have that. So by the time I'm going back to my own history here, looking at a continent like Australia, we have several thousand of densely sampled earthquakes covering this continent, such that when we project it onto some grid, we have a path density that is, you know, very, very dense, very, very well covered in some places, but here too, you know, a lack of density of sampling in some areas, and those are areas where we need improvement. But on the whole, that is all there is to the principle of tomography, being able to predict to a good first order what you should be expecting, carefully looking where to measure what is a misfit, and then, which is complicated and interesting, mapping that back onto where that structure needs to be adjusted such that we update our models, which sometimes takes the world's largest computers, like the people here are also doing. But in principle, that's what's going on. So here's just a couple of models here. This was when Torsten and I met in the Cambridge area. I was working on Australia, and my cocktail question answer to the question, what do you do and why do you do it, is, well, imagine that you're in Australia and you dig a hole. Where do you no longer know that Australia is above you? Where are you in the mantle? Where does that thing end? Is Australia an island or a continent? That was the question I got at, you know, weddings and funerals. Okay, so you take a look, you make a cross section of a shear wave speed anomaly with respect to some average, and then you're seeing, well, if I'm plotting the faster than average blue and the slower than average red, well, there is a clear definition to the continent. It really does look like a floating keel of a ship that floats through the mantle, and where it's red, I like to think of mantle material, and where it's blue, I like to think of continental material. And then there is the geology and the mineralogy and the geodynamics that comes into play in explaining why it's like that. Where is it going with that? What sort of shape it used to have, might have had, will have in the past. And in that day, we were looking with much interest at the correlation between what we indeed saw in the subsurface geology that told us something of the surface geology. Economic geology in Australia is about diamonds, among other things. And so diamonds form at certain depths under certain conditions and certain temperatures and certain pressures and certain oxygen fugacities and certain materials, and you need to have a look inside to make certain predictions. So that was indirectly motivating our investigation of this sort of structure. Back in those same days, my office mate was modeling subduction zones. And one of my first introductions to global seismic tomography was the work of Professor Grant here in this department, who, with my advisor, Rob Vanderhilst, wrote one of the papers that says, hey, look, you've been doing your thing, and I've been doing my thing, and we're seeing some of the same things about subduction zone structure. And that was really a very important moment in this field. So a few years later, all the blue things are things where we think and call them subduction zones with some question marks here. That's where this stuff is going down into the mantle. Sheet-like drips, if you will, of strong, coherent, maybe somewhat colder, maybe somewhat more water-rich in their tops, pieces of material that, due to surface tectonics, are forced inside of the mantle and contribute to the wholesale recycling of the material inside. So this is an example of how the structure of the interior of the Earth, as revealed by seismology, contributes to the global understanding of plate tectonics and the overall geology of the Earth. Here's a much more recent model. This is now a decade later, if not more, and this is an example of a model that literally has used one of the world's largest computers, I don't know, maybe top 5 or something, in some fancy national lab, to work through thousands and thousands of earthquakes over, well, a few thousand earthquakes, over altogether thousands and thousands of records to produce many, many tens of thousands of observations, all of which are tried to fit inside a picture. And here this is some cross-section. It's not a cross-section, it's a depth section. So at a particular depth of 250 kilometers down into the Earth, the warm colors, once again, are slower than average wave speed, and the blue colors, are cold colors, are faster than average wave speed. And so here, the places underneath Hawaii and the Galapagos and various other places are outlined because the stuff going down in the Earth, the blue subduction zones, those sheet-like downwellings, well, the return flow comes in the form of plume-like upwellings, and seismology is still on the hunt to find the proper, well-resolved expression of mantle plumes on the inside of the Earth, and our imaging has gotten ever better. This is by no means, even though it's published, and this is work by Ibru Bozdag, who's now at the Colorado School of Mines, a finished model. This is, in fact, their 15th iteration of something that will need a few more as data are continually assimilated, and this is a place of computational seismology and geophysics, together with its tectonic interpretation of the subsurface geology, where our field is really making a lot of progress. This said, we are never going to change where earthquakes are happening, even though people in this state and some other states are actively trying and making earthquakes by wastewater, well injection, all sorts of things on purpose, and have been doing it for a long time. There's no mystery or mistake about it. We're just not able to generate the magnitude 7 that really are sending enough energy down into the Earth to travel hundreds of kilometers down to come back up thousands of kilometers away. There is still some work to do there. So we don't control where earthquakes are happening. Here I'm just plotting 3 days in 2007 or something. This is about 3 days worth of earthquakes that show up in the global networks. And not surprisingly, it's once again the favorite zones, the zones of active subduction, tectonic strike-slip motion, subduction motion, continent-continent collision, more subduction, the odd ridge earthquake, and then the odd other earthquake. These are all relatively large earthquakes. These are of the type that are good to image the interior of the Earth. that are recorded by multiple stations on standard global networks. In other words, that's the type of earthquakes that we like. We don't, well, we in general like earthquakes. We don't like the very, very large earthquakes, not only because of the human suffering, because they're very complicated, often have long ruptures. We kind of want to keep the magnitudes 5, 6, 7, let's say, that we can still consider to be point sources that we can well model by coming from somewhere and going to somewhere, so we can do our tomography without too much complications from the finite rupture, which by itself would be interesting to study. Here's a picture a couple of years old, but this is not a rapidly changing map here of the global seismic network. Seismology is in a great state. It's a very well coordinated science of people who have decades of experience with, I can't call it big data, because then the big data people would say it's not big data, but it is much data, okay? Large data for years and years and years. Large data has been collected and very carefully archived. Any one of you, as in helped with the tools that some of you were showing me today, can request data from all sorts of places all the time and really start and get to work with high quality seismic data. IRIS is one such purveyor of that sort of well organized data archiving. Obviously the USGS and other places. And you just take a look at the map and you're seeing, well, geography, dry land, islands, and colonialism, where people have had colonies. That's where the good stations are, and where the weather is nice, people go. But then there's a lot of blind spots. So blind spots to a tomographer are not just the spots where there are no data, but the stuff where on the path connected by an earthquake through the interior of the earth, possibly bouncing off the surface, coming down again, and then hitting the station, where it sort of doesn't contribute to knowledge in specific places. So it's not as easy to say that, oh, we haven't been there, there is no information, because there will be surface waves going through, there may be bounce points of waves. But on the whole, here in this map, this one was made by Rafa Montelli a while back, it's just saying, okay, let's just gray shade where there is not very much information, and we can go into detail what that means for information at depth. Just another rendition of the fact that, if you don't know it by now, we need to go to the oceans with our seismic stations, okay? We do need to go to the areas where we have never sampled, because then even with crude tools, we will get new information. Shining a flashlight in a room that has never been lit before is going to be useful no matter what. So we, in 2002 or something, took inspiration from an oceanographic project that has since grown to more than 4,500 floating devices in the oceans. I took a snapshot here on St. Nicholas Day 2007 when it had hit 3,000 floats. Okay, so the oceanographers want to know, where is my ocean, because it's going in places because of salinity and density and thermal currents. They want to study the let's call it some surface layer, some upper, they could go deeper if they wanted to, but collecting physical and potentially chemical information about the oceans as they are moving around in the big ocean currents. That was the big objective of the Argo float. And so they got together, decided on a standard, invented the technology for it, and in a decade or so they were at 3,000 floats. And every day, you can go to their website, that picture obviously changes. Some of them die, some of them are newly put in. But every day, they're somewhere else. And so they're passively floating with the oceans. So we thought, if we could only maybe have, I don't know, a tenth of that, 300 floats, and instead of taking physical or chemical measurements, have them take seismological measurements, we'd be doing well in improving tomographic resolution. And I didn't mention at all the concept of ocean bottom seismometry, which I also know that various of you are engaged in, because we didn't we specifically know that that's the solution to get stations in the oceans. That's to go there and put them on the ocean floor. But that's expensive. And that's expensive in terms of time and effort and technology and ship time to get there. And if we're never going to be quickly ramping up from 0 to 300 ocean bottom seismometers, we'd get 30 at a time, 50 if we're lucky. It's very complicated to do ocean bottom seismometry, and others are doing it, including some of you maybe in the audience. So that's all great, but that's not what we wanted to do. We wanted to do something that was quicker and admittedly dirtier, but that had much more global coverage and could be done much more cheaply in terms of money, time, and effort. So that was our question. Can we build something that even remotely resembles the freely floating robotic exploration of the ocean in the Argo project? And yeah, we can try, okay? Well, that was 15 years ago. So my then postdoctoral advisor, Hust Nolet, always clever at coming up with acronyms, came up with this one: Mobile Earthquake Recording in Marine Areas by Independent Divers. Yeah, that's a good one. It spells Mermaid, and that's the name of the program. So if I started right away with our first prototype, somebody would say, well, surely that idea wasn't new. And of course it wasn't. Like all good ideas, there's probably 3 ideas in the world, and they're all recycled in various forms. So also this idea had a long history of people trying to get more instrument in the ocean. So even in the 1970s, when the first wetsuit was barely invented, that same guy, actually, Bradner, invented some kind of a freely floating sphere that would have a 3-axis, 3-component seismometer and a tape, if you still know what that is, on the inside, and a clock radio, and in other words, 1970s technology, and it recorded a variety of earthquakes. This is a project from Scripps, and here this was their mid-water seismometer, triaxial seismometer, aluminum pressure housing, amplifiers, clock, and so on. So what do you guys think is the main reason that this great idea never worked? Looks like in 1970 somebody already knew that we'll need to go to the oceans and we'll put a seismometer inside of some pressure vessel and it'll float, and then it will, pick it back up and read the tape. Power is always an issue and remains an issue. So where is the power going to come from? We will talk about that. But when you're doing seismology, recording waveforms, that's all good and well. Keeping time is important, and knowing where you are is even more important. And clocks were good, but they didn't know where they were. There was no way of telling where this instrument was. So it had to be close to a ship, or they had to echolocate it, or they had to do it. So there was no GPS. They really had no way of keeping track of the instrument. So it never floated. Another sort of thing from, shortly thereafter by some of the same people and then some other were sonobuoys. These are still used by I'll say Navy, but maybe that's not the right word. People engaged in marine warfare to locate submarines and ships. They will throw short-lived hydrophones that record pressure variations in the water to listen briefly until, oh, there it is, and then they report the location of whatever submarine may have passed by. So those are called sonobuoys. And so in this record, also from the 70s, trying to retrofit that technology for seismology, you see a little P wave and you'll see the little S wave, and there is a T wave, which, if you don't know what it is, it's an earthquake wave that comes from somewhere, travels as an elastic wave through the solid earth medium, and then hits the ocean bottom, gets converted into an acoustic wave in the water, and then hits land again and gets converted to an elastic wave, and then shows up on a land seismometer. That was the original T wave. So it's a tertiary wave, which, well, I can't really see it very well. And so this old technology also had some promise, but it was just very, very noisy back in the day. And so this too didn't really float. However, they kept better track of location because they were more actively engaged in radio exchange with it. And then in the 90s is when the oceanographic technology was really sort of maturing, and there was a floating device called a swallow float, which was made by a person named Swallow. And my then advisor, Houston Olet, looked at these records. And so here's a time trace of one of those swallow floats that was carrying a hydrophone. And right where, due to a known earthquake, which was observed on many other stations, we were expecting, or he was then expecting, a P wave. You're seeing a slight increase in the amplitude here, a slight change in the frequency content. And when you map all that onto the time frequency plane and you contour the amplitude, you indeed see the arrival of energy. And here too, this was crude, but it showed that it could work. It showed that a freely floating, cheap hydrophone, they barely cost $300-400 if you're getting a good model, that would just be completely passive, was in principle capable of recording an earthquake that's at a respectable distance, 47 degrees. That's 5,000 kilometers away. That's not nothing, so that's a reasonably good mantle sampling. So that was 1991 or 2 or 3 or something like that, and then that idea just sort of stayed until that guy who discovered that thing on that instrument and I started working together, and we built this first generation Mermaid roughly between 2003 through 2012. And here's the story where the little guy can't do anything because we had very little money. We had this idea that in principle it should be tried. We built one with help and with some scavenged parts, and the government gave us just a very, very little bit of seed funding to try it. Nevertheless, it was good enough to buy one of those solo floats that was in current use in oceanography, and to buy a hydrophone and to put it on the side and mount it and then work on the data recording package. And so here you see the inside of that thing. It has a bladder and pump system to adjust its buoyancy. It can go down from the surface, where it doesn't record any earthquakes, but it knows where it is and can transmit data, to some depth, where it doesn't know where it is, but it can keep time and it can listen for earthquakes. And when it then discovers an earthquake, thanks to the brains that we build for the instrument, it can then adjust its buoyancy to come up and report that earthquake. That's the whole principle. Freely floating, no cables, no anchor, not at the bottom, but somewhere in the middle of the water column, always listening and doing the pattern recognition that will distinguish an earthquake from whatever other noise there is. So that instrument flew, or went somewhere in 2003 and 2004, and here she is, in action. And we recorded precisely one teleseismic earthquake in 2003 or something, and it took us a few years to report even that one. So that was the very first ever proper earthquake, magnitude 5.95 at about, again, 47 degree, recorded on board of our little Mermaid -001. And so here we were going up. This is a promising technology. And then I wrote 6 rejected grant proposals that were all excellently reviewed, thank you very much, but didn't get any funding. And so we kind of, kept playing with it. That's only funny because in the end it ended up working. But also while we were at it, we just decided to do other things, First of all, while we were building the technology to do this sort of thing and we didn't get any money to build it or deploy it, we decided to work on earthquake early warning because it's the same problem. What of an incoming data stream do you listen to? How do you condense that information into something that tells you there's an earthquake and what type is it? Is it worth it? Is it worth reporting? So all these algorithms that we had to do, whether they were applied in real time or not, they were in development, and that's free. So by the time we managed to do a few experiments, here are a few of the records early on by that very first prototype. This is where I make it interactive and let you guess what A, B, and C are. So what's A? The first column is time domain, so it's just acoustic pressure in the water. Up is more, down is less, doesn't matter what the scale is. The second panel is a time frequency plot, which tells you where approximately in time, approximately which frequency is approximately how loud. That's the color. That's a variation on it, which I won't talk much about it, and that's the overall noise. Rather, it's the overall power spectral density of that picture on the right. So that's essentially the sum total of all these things over all of that time. So what do you think is this? Any suggestions? What in the ocean appears loud and appears capable of growing and decaying on a time scale of some freely floating instrument being in or near, and has decidedly horizontal structure to its time frequency spectrum, something that has frequencies at which it keeps going even though it gets to be louder and then not so loud? What is it? It'd be a very harmonious marine mammal in that case. It's a ship, right? It's the churning at a rate of a size of a screw that will just come by. Then what is that second thing, which is very periodic, as in on a schedule it appears, and the structure in the time domain is vertical, as in spikes this way, which are also, of course, showing up in the time frequency domain. So what in the ocean is making that sort of noise on a schedule? Pirates? Tides. Tides, we'd be lucky if we got those. Are much, much slower, smaller oscillations. This is at a faster rate. You probably don't know what the scale is. It's in seconds here, not tides, but that could be. So what that is the timed implosions of an air gun that is doing active exploration offshore. It's bang, bang, and then, you know, all night long. Number 3 here, what sort of thing has a emergent arrival that's sort of, you know, getting louder and then not, and it's clearly not a ship because it doesn't have that horizontal structure, and it's clearly not an air gun because it's not spiky in the time domain. Unless you already knew it, you wouldn't. So that is one of those T phases, which is some energy from somewhere, earthquake has been converted to some seamount somewhere and is like rolling inside a sound fixing and ranging channel, which very efficiently propagates it, but it's become this diffuse rumble that comes on, and that's not useful for us for seismology because it's very hard to, for our kind of seismology, it's very hard to pinpoint to where that came from. All right, mammals, here are the mammals. They're also there, okay? So the singing and clicking and harmonizing and vocalizing of the various whales is very clearly in those records, and it's also never mistaken for a seismic event. They're in a too high frequency range. They have very interestingly modulated patterns, none of which look like the thing we were after. The thing that we were after, and that was that first record that you saw, again, but now it's not filtered, is right here in the time frequency plane. Is very low frequency, maybe 1 hertz, half a hertz, and it's just this, it's actually very noisy, so it's already red and then it gets to be a little bit redder. But nevertheless, it shows up clearly in a variety of renditions. And so a large earthquake relatively far, a small earthquake relatively close, we were starting to detect earthquakes. So that was all the record that we had to run on. An instrument that existed, a handful of experiments going on the ship, about 150 hours of data that took us a while to analyze and build all the routines for, but nevertheless, it was there. And here are more examples of earthquakes. Clearly, I don't spend time trying to read the graph other than its axes. We are interested in how far, how large an earthquake is, and that we can still detect it in the oceans. A big, loud one can be farther than a small, which has to be a small one, which has to be close one. Where to draw the boundary, that was for a long time to try to get to where that boundary lay. Then is the process of science here. Then my advisor, with whom I was doing all that work, moved to Europe and got all of that money, even though it was in euros, and I actually physically normalized the areas to the money that I got. Okay, so that was the senior hire going back to Europe after a distinguished career and getting a ton of development money, and that was me to scale. And so anyway, I continued to work with him. That was clearly the smart move to stay with the money. But it's a sign, perhaps, of whatever it is a sign of, is that it is very hard to get research money to build something that doesn't exist and that may not work, with a record that, kind of gets there, and then people say, that's a great idea, but it can fail. Yeah, that's so. As a motivation here, don't let that get you down, because there's a lot of other things you could do. So we managed, thanks to all of those bundles of cash stuffed in various suitcases that went to Europe, to get a French company interested in building the next generation of Mermaids. And so they just changed the color, essentially. More or less the same design, slightly different antenna, different hydrophone, slightly larger. And suddenly it was in production. And they went to the Indian Ocean, to the Mediterranean, to the Galapagos, to there. Some 20 odd have been around as part of the second generation. Here is one of those emerging in the Bay of Villefranche in France, where Husnolet then was working before he now ultimately retired. And so again, a couple of years later, with a new collaborator this time, well, now we have a whole catalog of earthquakes, small and large, of P waves and core waves. In other words, waves that come from one earthquake and go through the Earth's core and come back all the way at the other end, the PKP and the PKIKPs and the little Ps, and so PPs, the bounced waves. And yeah, surely there's certainly still some of them are noisy, but these are relatively unfiltered records, and clearly that's part of the game, to process that into clear arrivals and then to do their timing sufficiently to do tomography with. But the two columns on the left are just a smattering of the various good earthquakes that we've been recording with this sort of second generation technology. And then the column on the right by itself is interesting, because it's just, what is it, 5 examples of a swarm of earthquake that ultimately generated 300 records of this type, of an earthquake that wasn't known about anywhere else because it wasn't large enough to show up on any of the land-based stations on the global networks. And it's just one example of seismicity that, of course, we know and suspected, but when you are nearby, you're picking up on the ocean ridges that are doing their thing. And so this leads to, it's not just making more records of known earthquakes to illuminate parts of the Earth that we haven't previously been able to resolve, but it's also picking up on the snap, crackle, and pop of whatever the ocean tectonics is doing that generates earthquakes, sometimes hundreds in a few days, that if the instruments are nearby, which chances are they will if they're going everywhere all the time, it will be picking up. So each of these seismograms is one of such example where the instrument was at depth, sitting there, floating passively with the currents, recording everything, deciding on the fly that something probably wasn't an earthquake until it was, and then deciding to come up and report the data, report the location, report it last time, readjust the clock for drift, and then just go back on its merry ways. If you want to be then going back to the tomography and say, well, let's just now play this thought experiment and do one of these classic checkerboard tests where here's the stations that we have, here's the stations that we might have, how would an input-output experiment get to be better? 700, 1,300, 2,300 kilometers. no, the Earth does not look like a checkerboard, so it's not a great test. But if the Earth looked like a checkerboard of faster and slower velocity, and you pretended you had the earthquakes where you have them, and you pretended where you have the stations that you have them and where you want them, and you do all your business of inversion more or less, then with this on the left type of data set, you're left with plenty of blank spots of poorly resolved areas in the Earth's mantle, okay? 700, 1,400, 2,500 kilometers depth. And if we had 1,000 mermaids, now admittedly it's a very optimistic figure, but we have a figure in the paper 300 and 100, well, you just put them in random locations and let them go, then clearly we can start to illuminate a lot more of the Earth and getting good return on our inversion input-output tests. 300 is the number I like to use now because I think it's achievable at the costs of buying them and deploying them. It's not that expensive compared to all sorts of other things that you could do which are much more expensive. Okay? So since last year, when clearly I think we had shown that the prototypes worked and the new technology with the French money was actually working very well, thank you very much, now we're into new avenues. Now we need to scale it up to a new size, essentially. Going from 20 to 200 should be the goal. And since last year, the company has the company that we work with, which is just a group of engineers who thought this was cool. Okay, so far they have not made any money in it, but they made a new design that is supposed to live for 5 years, that can go down to ultimately 4,500 meters depth, that has a little bit more of the bells and whistles, and it's no longer that solar float that we stole from the Argo community, but it's rather a glass sphere with some electronics inside, some antennas on the outside. Here it is being tested in the lab. Here is the inside with battery packs. So that instrument right now is the one that you can go to the shop and buy. Okay, they don't have them ready for you because they only build them when you buy them, but it is now a technology that we can have. And so my university has committed to buying 10, and that's not that large of a number. The Japanese have bought a few, the Koreans are buying a few, the Chinese, if it all works out, will buy a few hundred, and so hopefully our goal of populating the oceans with new instrumentation, preferably with other people's money, has been, realized. Still, that's not enough, and so the fourth generation, which is in the future, is supposed to really be realistic about the fact that the world is full of people who aren't seismologists, and recording our little earthquakes is just not of enough interest. But while we're sitting there, we're recording whales, we're listening to the sound of rain, which actually is surprisingly hard to correlate with actual observations because nobody has a rain gauge on an ocean. And in fact, the acoustic trickle of that rain is very distinctly measurable using even our instruments at depth. So our current push is to increase this sort of technology to just be a data port for whatever miniaturized instrument that other communities may do. And so the next generation, so this is no longer, this is a prototype now, this is going to be called multi-Mermaid. It'll have extra space for your instrument, for your chlorophyll sensor or your conductivity, temperature, depth, in fact, as we are doing ourselves here, or whatever your sensor is, pH or oxygen or something, it'll just fit in there in that shell that you have seen. So that's coming. It'll carry other people's experiments, and we just want to get right over the edge where we're in there. We're in the oceans, and if you want to come along, you could design your own module to have a data port that can plug in there. We'd like to go back to this Argo community and see, hey, look, we're using your CTD, which costs, I don't know, $8,000, even though you can make your own for $2,000, but it has to be theirs, so it's standard. and you could, conduct our seismic experiments at the same time delivering data for oceanography. And then the very last thing I'm excited about is this thing here. There's a company called Seatrek, which is by, a person who has a patent on a thermal recharging system, which I'll show you the next slide. This is a slide from him here. It's essentially just mining the energy that sits in the thermal gradient as you go, from sun to the darkness of the oceans. And so if you can store and release and chemically to electrically transform that energy fast enough, backwards and forwards, you have essentially indefinite lifetime to this instrument. And not only is it an indefinite lifetime, which is obviously good for science, but it also, of course, it's clean. It's a green solution for an environmental problem to begin with. And so we are hoping that next year we'll be able to buy one of those batteries and adapt it for this sort of instruments and then use it. So back to the old conclusions, we want to know the structure of the Earth and how it's deforming and has deformed and how it ultimately is changing state, of which we see today's snapshot. And we're going to do it by looking at measuring things seismically, gravitationally, topographically, and that's going to come ultimately because it maps the temperature and composition of the Earth. And one of the techniques, seismic tomography is one of those, and drifting recorders, which are a long way from an aluminum tape recorder in a box that didn't know where it was, but that still sort of has all of the elements of it, is what we are trying to push for, not just for seismology and subsurface geology to bring it back there, but also for meteorology, biological oceanography, chemical oceanography, physical oceanography, and various other fields that need something done in the oceans. Thank you.
Thanks so much, Frederick. We have time for questions.
Orders, one. I'll put you down. Yeah.
Does this internal energy device allow the Mermaid to go deeper and record at better resolution?
So the depth is ultimately a factor of two things. First of all, it does need energy to go to depth. To come up from depth, also, it's like there's time involved in going. So for seismology, the deeper it is, the longer it is between an earthquake is recorded and it's at the surface where it knows where it is. So there is a lateral drift that seismology can't make too large. Oceanographers, that doesn't really matter that much, because if it's 2 kilometers away from where you started, you're still in the right space of the ocean, so by going deeper. So the new depth isn't actually a function of the new battery, but it's a function of other improvements to the materials, the pump, the energy balance and budget. But clearly, more energy means you can go more times to a larger depth, because in fact you purchase an instrument in terms of cycles. It'll be 200 cycles down to 2 kilometers. That's what you're buying. That's what it can do in a normal gradient. Yeah, but so deeper for seismology doesn't necessarily translate into better, because there's other factors. Yeah. Yes. Yes.
So how many of the third generation Mermaids can you buy for seismology?
So 30,000 euros will buy you a third generation, and the deployment, if you are friendly, could be free, because all you have to do is hit somebody up that's going somewhere and say, just like 3 of those boxes, can I just drop them? And then you'd have to pay room and board, and that essentially is free. A classical ocean bottom seismometer, there's people in the audience that know much better than I, but let's say it would be, I don't know, twice the acquisition cost, which would be dwarfed by the number of ship days you would have to devote to bringing that to the Indian Ocean and back, which could run, I don't know, 60, 70, 80, $90,000 a day, because you're taking a crew of cooks with you and cleaners, and it takes time. So the cost savings here are not, even though they are in the instrument, that's not where the costs lie. The costs lie in the deployment and recovery costs of going out at all into any of the oceans. And that's where we're hoping to really save Yeah.
Good question here.
When the mermaid's at depth, how to know its location precisely?
So this one, what we do is it doesn't at depth. We only know its locations between two surfacings. So while it's at the surface, it waits for a GPS signal, it resets the clock, and it knows where it is. Then it goes down until it hits an earthquake. In this time, it doesn't know where it is at all, but we know something maybe about currents. Next time it finds an earthquake, it comes up, and then we know again where it is. So we're doing the experiment where we know between surfacings how long it's been taking, and here's where seismicity rates help us. We have a useful potential earthquakes every few days, and at certain depths, even with the additional currents from being at the surface, our tolerance for that drift is just right. Well, it's just happily not optimal, but it's just good enough to not really worry too much about. So it doesn't know where it is, but we know with sufficient precision to do seismology where it is, and we certainly know that location to sufficient precision for oceanography or other areas where the time and distance and location don't matter that much compared to seismology.
Frederick, about your resolution test, what's going on there?
So this is just a geometric experiment where you're doing a classic input-output test with some checkerboard structure, some set of earthquakes.
Way too good under the oceans, and what was happening with Africa?
Well, so this is 1,000 mermaids in random locations, and so given the earthquake station distribution to and from wherever to wherever, it turns out that the oceans don't actually help very much with mid-mantle depths under Africa.
Can you show again? I don't believe it.
So the active sources are, where they're at, right? The large, where is my pointer here? So so for orientation, here's South America, right? And then the Aleutians and the Philippine Sea. And so yeah, you'll get some mermaids here, but ultimately, and these are just first arriving PWAs. So you could say, is it so bad you don't believe it, or so good you don't believe it?
Both.
Both, yeah. So this is just a geometrical inversion experiment with just P waves, with just some more mermaids in addition to just the ISE stations with the current coverage. Now that's just, it's more than a cartoon, but it is a completely hypothetical experiment that nevertheless is what you would get if you did only that. And yeah, it doesn't actually help much in mid-mantle under Africa.
So unfortunately, we have a large organic chemistry class that's going to flood us in here.
I need to teach that?
So, but let's thank
This is a figure I was wondering, should I really show it? Because it's an experiment that's not realistic, but it is the experiment.
But I think there's something.